You've seen the movie scene. Hero sprints away from the explosion, dives, fireball rolls past overhead, everybody's fine, roll credits. Now imagine that scene, except the explosion is a star. There is no version of that scene. None. Not because you're not fast enough, because outrunning isn't even the right word for what a supernova does. So let's actually figure out what it would take to run from one, the real numbers. And I promise you, the real answer is stranger and worse than the movie ever showed you. Here's the instinct everybody starts with. Something explodes, you run away from it. That instinct isn't wrong exactly. It's just built for explosions you've actually lived through. A grenade, a gas leak, a firework going off too close. Things that happen in one spot, throw force outward for a few seconds, and then it's over, and the air goes quiet again. A supernova doesn't work like that. It's not a burst that fades. It's the sudden, total collapse of a war a star has been fighting against itself for millions of years. Gravity pulling inward the whole time, fusion pushing back outward, holding the line. And then, all at once, the core loses. It collapses in about a second, an entire stellar core crushing down almost instantly. The outer layers of the star slam into that collapsed core and rebound outward in a shockwave. And that shockwave doesn't fizzle out after a few seconds like a grenade would. It keeps expanding, plowing through space for thousands of years afterward. You're not trying to get clear of a bang. You're trying to get ahead of a wave that has no intention of stopping anytime soon. So let's get into the actual mechanism, because the numbers here are what really start doing damage to your intuition. When a massive star's core collapses, the shockwave that blasts outward moves in the earliest moments at a real fraction of the speed of light, tens of thousands of kilometers per second. That's not a metaphor for fast, that's genuinely close to relativistic speeds, right at the start. Over time, as that shell expands and plows into the surrounding interstellar gas, it slows down, like a fast car losing speed the deeper it drives into thickening mud. But in the first hours and days, it is moving at a pace nothing you could ever build would outrun. Except, and here's the part that changes the whole question, the shockwave isn't even the thing that kills you first. Work out the actual distances. The deadly zone where radiation alone would sterilize a planet, no shockwave required, no debris required, just light and high-energy particles, extends out to roughly 25 to 50 light years from the star, depending on its mass and exactly how it explodes. And that radiation travels at light speed, which means it reaches you at the same moment you'd first see the star brighten. There's no gap. There's no warning flash before the real danger arrives. The light gets you before the shockwave ever could. Because the light doesn't give you a head start to run, it doesn't give you any warning at all. You'd look up, see the star flare unusually bright in the sky, and that light hitting your eyes is already the danger. Not a preview of it. The thing itself, already arriving. So if you're within that kill radius, running doesn't just fail, running was never actually an option, because the moment you'd know to run is the same moment it's already too late. That's worth sitting with. It breaks the entire premise of outrunning something. You can't outrun information that travels at the fastest possible speed and only reaches you the instant it's already doing harm. Now, how far away is actually safe? Here's where I have to be honest with you, because this is exactly the spot where good science stops giving you one clean number and starts giving you a real complicated answer instead. Astronomers put the safe distance from a supernova somewhere around 50 to 100 light years, depending heavily on the type of star, the geometry of the explosion, and which specific danger you're modeling, gamma rays, X-rays, or the slower physical shockwave and debris arriving later. Picture it like layered rings around the exploding star, an innermost ring where you're dead almost instantly from radiation, a middle ring where you might survive the initial blast but face long-term damage, think ozone layer stripped away, years of increased radiation reaching a planet's surface, ecosystems slowly collapsing rather than vaporizing outright, and an outer ring where you're essentially fine, just watching a very bright new star appear in the sky for a while. But here's the honest complication, the part I don't want to smooth over just to give you a tidier ending. That safe distance number isn't one settled figure agreed on by everybody. It shifts depending on which danger you're weighing. There's a specific, more violent subtype of stellar death called a gamma ray burst, tied to only a small fraction of exploding stars, but ferociously more dangerous than an ordinary supernova, because the energy doesn't spread out evenly in all directions. It fires out in two narrow, concentrated beams, like a lighthouse instead of a light bulb. If one of those beams happened to be aimed directly at a planet, it could sterilize an entire hemisphere from thousands of light years away. Thousands. Not 50, not 100, thousands. And here's the honest gap in our knowledge. We don't have a complete model for exactly how often these gamma ray bursts happen, how their beams get aimed relative to any given planet, or precisely how many nearby candidate stars could ever produce one aimed our way. We can calculate a shockwave speed with real precision, down to fine detail, but we cannot tell you with full confidence exactly which nearby stars are truly safe, because some of the deadliest supernova types depend on a targeting question, which direction the beam happens to fire, that we don't fully understand yet, and in some sense can't know in advance at all. That's not a failure of the science. That's the science being honest with you about where it currently ends. So here's what I actually keep circling back to every time I think this one through. You can't outrun a supernova, not because you're slow, not because no ship could ever be fast enough, but because the explosion arrives as light before it arrives as anything else, and light is the fastest messenger that exists. There is no early warning system in the universe faster than the danger itself. The thing that would warn you and the thing that would kill you are the exact same signal, traveling at the exact same speed, arriving at the exact same instant. Zoom out from one star to the whole galaxy for a second. There's a small handful of known massive stars close enough to Earth that they're worth thinking about. Not close enough to be an active threat right now, as far as we can tell, but close enough that astronomers keep an eye on them anyway. And when you actually map that out, when you look at how thin the margin really is, you start to notice something worth sitting with. Every living thing that has ever existed on this planet has done so inside a specific, quiet stretch of cosmic luck. Far enough from any nearby star's death, for long enough, uninterrupted, that complex life got the chance to happen at all. Not because Earth is protected by anything special, not because there's some shield around us, just because, so far, the geometry has happened to work out. You can't run from a supernova, because there's nowhere to run to that the light hasn't already reached first. All you can really do is already be far enough away before it happens, and that's not something you control, or plan for, or prepare against with any amount of speed or cleverness. It's something you simply already are, or you already aren't, decided long before you ever knew to worry about it. Right now, tonight, you're sitting inside a universe that decided so far not to put a dying star close enough to matter. That's not a law of physics guaranteeing your safety. It's not a rule anybody wrote down. It's just how the map happened to be drawn, this time, in this corner of the galaxy, for exactly as long as it's lasted so far, and not one bit longer than that.